Hello, my name is Julian Bernhard. Me and my colleagues are from Fortis, the research institute of the Free State of Bavaria for software-intensive systems located in Munich, Germany. In this work we introduce BARC, an open-source behavior benchmarking and development environment tailored to applications in autonomous driving. The overall motivation for developing a new behavior benchmarking environment, BARC, was that interactive behavior generation is not yet robust against inaccurate predictions. Mimicking interactive behavior when interacting with human drivers is a long-standing challenge in the development of decision-making for autonomous vehicles. An example for very complex interactive behaviors of humans is seen in the picture on the right, showing a crowded intersection in New York. The problem is that errors in the prediction due to incomplete and faulty models can have catastrophic consequences in real-world driving situations. It still remains unclear how to systematically understand what effects inaccurate predictions have when employed in interactive behavior generation algorithms. We claim that to systematically improve applied behavior models in the domain of autonomous driving, it shall be possible to use prediction, planning and simulation models exchangeably in a benchmarking framework. We therefore developed BARC. In BARC we can use the same behavior model implementation to plan the ego motion of the autonomous vehicle, being the model to be benchmarked. Predict the motion of other vehicles in a planning algorithm relying on predictions, such as Monte Carlo tree search, and simulate an agent in a purely virtual environment during the benchmarking process. For this, BARC provides a pool of behavior models which can be assigned freely. For example, a traffic model such as the intelligent driver model can on the one hand be used to populate a simulation with agents, but also as a generative model to predict other agents' motions from the viewpoint of the ego vehicle. A Monte Carlo tree search planner can be used to plan the motion of the ego vehicle, but also to control other vehicles in the simulation. So how does BARC work in detail? BARC's simulation concept is as follows. Experiments in BARC shall be fully reproducible, independent of the frequency at which the simulation runs. To ensure this, BARC models the world as a multi-agent system with agents performing simultaneous movements in the simulated world. At fixed discrete world time steps, each agent plans its behavior using an agent-specific behavior model which only has access to the agent's observed world, but not the simulator's simulated world. The concept of simultaneous movement ensures that a behavior model can plan based on reproducible input information. It avoids timing artifacts that may occur in message-passing middleware-based simulation architectures. The BARC world model contains the map, all objects and agents. Static and dynamic objects are represented in the form of object lists. We will refer to dynamic objects as agents in the following. The observed world model, on the other hand, reflects the world that is perceived by an agent. BARC's observed world model accounts for the fact that the observing agent has no access to the true world behavior model of other agents. BARC can model different degrees of observability by either completely restricting access to the world behavior model or only by perturbing the parameters of the world behavior model as shown in the upper right picture. An agent in BARC provides two main interfaces. The behave interface generates a behavior trajectory being a sequence of desired future physical agent states. The execution model determines the agent's next state in the world based on the generated behavior trajectory. An additional execution model allows to systematically examine the robustness of behavior planners against execution errors. Based on this simulation concept, BARC provides a benchmarking workflow. The scenario and benchmarking concept of BARC is as follows. A BARC scenario contains a list of agents with their initial states, behavior and execution models, as well as a goal definition for each agent. Goals can, for example, be to move into a certain region or lane. Further, it contains a map file in the OpenDrive format. To support behavior benchmarking, each scenario specifies which agent is considered the control agent during simulation. BARC provides scenario generation modules for configuring sets of scenarios. The scenario generation allows to specify all agent models and goal definitions based on parameters. Different parameter sets can then be used to generate different sets of scenarios, for example with varying density of traffic or more passive or aggressive participants. The scenario sets for each parameter set are then serialized to binary formats representing a benchmarking database. Serialization allows for exact scenario reproducibility among different systems. BARC provides a benchmarking runner supporting large-scale evaluation of behavior models over a collection of scenario sets contained in the benchmarking database. The evaluation is based on an abstract evaluator interface calculating a Boolean, integer, or real-valued metric based on the current simulation world state. Evaluators check, for instance, if a control agent's goal definition is satisfied or whether any agent or only the currently controlled agent collided. The benchmark runner runs each scenario of the database evaluating world states of the simulation. It terminates the scenario run based on criteria defined with respect to the evaluators. BARC also provides a distributed benchmark runner to perform evaluations in parallel on multiple cores and clusters. Having discussed BARC in a nutshell, we want to show that BARC closes an important gap left open by other simulators. To systematically develop interactive behavior generation algorithms, we think that a benchmarking environment must fulfill 4 key requirements. It must be able to simulate interactions between participants, be able to exactly reproduce and deterministically simulate also for varying simulation speeds, it must provide benchmarking capabilities, and most important is the exchangeability of behavior models, allowing to perform parameter studies on inaccurate predictions, as we demonstrated experimentally in our work. Sensor simulation is not essential for this purpose. Compared to other frameworks such as Scala or Common Road, BARC is the only framework fulfilling our proposed key requirements. Thus, it closes an important gap in the development of interactive behavior generation algorithms. BARC contains a set of reference implementations for behavior models. Simplistic models are the very popular intelligent driver model, being a car-following model often used in microscopic traffic simulation. Based on this, for multi-lane scenarios, we implemented the mobile model, a decision-making entity to trigger lane changes. The adaptive cruise control model simulates more human-like car following. Our time-to-collision model supports intersections. We provide single and multi-agent Monte Carlo tree search implementations, being well-known tree search methods for finding approximate solutions to sequential decision problems via sampling. The implementations are easily customizable using different evaluators for reward calculations or by exchanging the used prediction models. We also provide reinforcement learning environments based on GIM interfaces and integrated the popular reinforcement learning library TensorFlow agents with several ready-to-use state-of-the-art algorithms. BARC also contains a dataset tracking model exactly following a predefined trajectory. This can be used to replay datasets. Currently, parts of the interaction dataset are integrated into BARC. All models are fully parameterizable in the scenario descriptions using JSON parameter files. Different behavior parameters can be sampled to generate different random scenarios. Next, we want to show 2 example use cases of BARC. First, we benchmark robustness of Monte Carlo tree search and reinforcement learning algorithms against inaccurate predictions. In our experiment, we consider lane changing in crowded urban roads. We sample 4 scenario sets with different parameter variations. The changing parameter is the velocity-dependent safety distance of the intelligent driver model. For example, the 40% parameter variation means that we decrease the safety distance 3 seconds of 0% variation by 40%, yielding 1.8 seconds. We employ the scenario set 0% for reinforcement learning training and use the intelligent driver model parameters of this set as prediction model such that we can evaluate how Monte Carlo tree search and reinforcement learning perform under inaccurate prediction models in the other scenario sets. Our evaluation over 200 scenarios in each scenario set and different numbers of search iterations is shown on the right. We show the percentages of each scenario run with the controlled agent reaching the goal, colliding or exceeding the maximum allowed simulation time steps, as well as the average number of simulation steps in the event that the goal is reached. It is clear that the collision rate rises as the prediction error increases. For 2000 iterations, the Monte Carlo tree search fails to explore worst-case outcomes, explaining the high success but also high collision rate. For 4,000 iterations, the worst-case outcomes are explored, yet no goal-reaching plan is found, yielding low collision but a large maximum number of steps. With a higher exploration at 8,000 iterations, the success rate increases greatly with a slight increase in collision. The reinforcement learning soft actor-critic model outperforms the Monte Carlo tree search model for 0% variation in terms of the success rate. However, when the other agent's behavior is different from that used in training, the collision rate rises more quickly. Our experiment showed that a systematic evaluation of behavior planners modeling limited knowledge about other agents' behavior is necessary to uncover and understand the weaknesses of both conventional and learning-based approaches in such settings. BARC covers the whole development lifecycle to tackle this open problem. Next, we show a use case of BARC where we use behavior planners for behavior simulation. We replace recorded behavior with BARC behavior models in replayed scenarios from the interaction dataset to evaluate how our current models can solve the interactive scenario in an open-loop simulation. We evaluate whether a collision occurred when an agent from the dataset was replaced with different BARC behavior models. In the table to the right, we see the evaluation results. We denote the set of replaced agents by A. In the evaluation, we do not account for all possible combinations of agents for replacement, but focus on 6 challenging ones. We established that, with the proposed tooling, critical scenarios can be analyzed easily. Algorithm fine-tuning is considered a subsequent step. We compare the performance of the intelligent driver model, mobile and single-agent Monte Carlo tree search. All 3 models use intelligent driver model parameters, as the longitudinal behavior of the mobile model is controlled using intelligent driver models, while Monte Carlo tree search uses an intelligent driver model as a prediction model of the other agents. We thus define 4 different parameter sets, P1 to 4 for the intelligent driver model. As we aim to provide a methodology for evaluation, we only vary the minimum distance without fine-tuning of other model parameters for this single scenario. The intelligent driver model is a pure lane-following model and thus not capable to perform lane changes. We thus do not replace agent sets A0, A1, A2 and A6 with the intelligent driver model. We observe that without fine-tuning model parameters, most behavior models fail to coexist next to replayed agents. The intelligent driver model can partially solve for A4, as it needs to retain sufficient gap distance from the preceding vehicle to let merging vehicles in. This is crucial as the order must be retained to prevent crashes further on in the scenario. Mobile can partially solve A0, where the agent has to change to the left lane. If the gap distance parameter is too small, the agent will try to accelerate and change lanes before agent 65. However, even if the lane change is executed successfully, a collision occurs at the end of the scenario due to the incorrect order of the vehicles. This shows the necessity to develop behavior models for simulation that are capable of handling more complex constraints such as maintaining a specific order. Although some mobile configurations can master A4 without collision, the overall scenario is changed as sometimes lane changes are triggered to go from left to right. All prediction parameter sets used in the Monte Carlo tree search successfully master the lane change of A1. Note that we do not constrain the final order of the SIP merge, therefore replacing agents in the left lane fails with Monte Carlo tree search. We conclude that current rule-based models, intelligent driver model and mobile, perform purely in highly dense scenarios as they do not model obstacle avoidance based on prediction of future interaction. More elaborate models should be investigated, as these allow constraints such as ordering and traffic rules to be modeled. Monte Carlo tree search can be used, but without an accurate model of the prediction, it also leads to crashes. Now, after you have seen BARC's concept of exchangeable behavior models and 2 applications of BARC, we hope we could convince you to just come by and check out BARC. BARC is open source under MIT license. We are happy to receive pull requests with your behavior generation algorithms and benchmark them against our planners. At our half-day tutorial at IROS 2020, we provide you with more details about BARC and will teach you how to implement and benchmark your own interactive behavior generation algorithm.